Good morning, everyone. I'm Avinaya Tripathi, a graduate student doing my research under the guidance of Professor Narayan Netilat. I'll be doing this presentation in his behalf. So in this presentation, I'll be talking about preliminary results. This is still a research ongoing, so the results are quite less right now, but it discusses about the thermal and structural performance of 3D printed sections when the infills are varied, like having hollow or stuff like that. So in general, right now, the research in 3D printing is gaining a lot of interest, while 3D printing itself is getting interest in like construction of different structures, majorly in walls for the sections like houses, like offices. Wall is the biggest thing that's constructed through 3D printing. Some are load bearing, some are non-load bearing. So these are some of the prints that we did at ASU for checking like overhangs and stuff. It's just a time lapse to show like what 3D printing can actually do. And the 3D printer that we have at our facility at ASU is a gantry-based 3D printer, which has a volume of about 2 meter by 2 meter by 2 meters. We have not gone that big, but again, that's the capacity we could most probably go to. So while printing walls, now the biggest thing we initially have to check is buildability to make sure that we can build to the height that we require. So we have built an analytical model at ASU to characterize buildability based on the green strength of the mortars. We use that model to predict the buildability for different mixes that we tried. We finalized 2 different mixes that we are going to use for the study. One is a normal strength, higher water cement ratio mix that goes about 75 MPa on 28-day strength. One is a high performance concrete, basically a low water cement ratio mix, which has a water cement ratio of 0.19 only, and it goes to about 110 MPa, and this is without the fibers. And the buildability for these 2 mixes were checked on a 25 mm thick wall, because right now we're going to print walls. So the buildability from prediction and experimental were close to around 40 for the normal strength at 30 minutes from mixing, while for the higher performance concrete, it was about 32 centimeters in 15 minutes after mixing. So these are some of the many patterns we tried. Single filament layer wall, 4 filament layer wall section, and it does not look like a wall again. It's a smaller section, yes. So, and V-type truss infill. We have like S-shaped infill. We have linear infills and U-shaped infills, which I have not shown here. But the first part was to characterize the conductivity of these structures, like how do infills work. So we did it with a Thermoflex 801. So for this, right now I'm showing you results for 3 of the sections. That's like the single filament, the solid, and the truss that I showed before. So this is the raw data that came from the machine, but again, this is padded between rubber pads. So we had to calculate the equivalent resistance of the section and then the conductivity of the section. What we observed is for the same thickness of wall, when we were doing a solid infill versus a V-shaped truss infill, we got a reduction in the conductivity. That's like around 25% at the lowest, and it has a significant decrease. Again, the conductivity will vary based on different average temperature of the section, so you can see the trend that it goes. But again, typical values for the conductivity are in the lowest spectra of the ones reported in literature, which are generally within the range of 0.5 to 2.5 watts per meter Kelvin. We are around, for the solid infill, we are in the range of 0.65 average, while for the other infills, we are in the range of 0.4 to 0.5. So another variation we tried for the normal, again, these are, right now, all these results are based on just the normal strength mix. We have not done testing on the high performance concrete right now. But when we are testing for the conductivity effect, one variation we tried is like incorporating phase changing materials. So phase changing materials being some sort of material that have that latent heat capacity. The PCM that we are using is a 25 degrees Celsius PCM, meaning it will change from solid to liquid by storing it at 25 degrees Celsius. This is a test ongoing. I only got 2 points from the results till yesterday, so I'm just representing those 2 results right now. So one thing we see is like the section that I'm showing here is a solid section for both. It's the same mix with one with 5% PCM incorporated, one without the PCM in. What we have observed right now is like there's a 25%, like the infill pattern gave us a 25% decrease, while here just incorporating 5% PCM is giving us a 25% decrease initially at lower temperatures. This is way lower than the phase change temperature for the PCM. We expect like as it goes towards 25 degrees Celsius, it more or less will go closer to the conductivity values for the solid as like the solid sections, which we see based on 2 points, but I'm not. This is what we assume, and we see that based on 2 points. We'll have to see further on the results to see if it actually does that. So that's more or less on the thermal conductivity part. We are trying to set up a thermal conductivity chamber to see actual heat change, as in this being a wall section for the room, and then do that. For the structural part of it, we have done some anisotropy quantification for different mixes and different layer heights that we do. This is for one of the work that we previously did. What we have observed is like typically when you have like multiple filament interfaces and layer interfaces, what we see is like the direction 2, which is compression, uniaxial compression along the build-up direction, which will be a typical loading scheme in a wall section, because that will be loaded in this direction. What we usually observe is like for different infill patterns and different printing patterns, we see like the direction 2 has a significant reduction in strength compared to direction 1 and 3. This has been consistent over the normal strength mix. This is like the high water cement ratio mix again. Now again coming to the low water cement ratio mix. Now this has like SP. So what it does is like when you are extruding it through the auger, the vibration, the movement makes it more flowable. So what we observed is like direction 2 does not have that effect, like the strength reduction is not there. This is again, all the experiments are based on a layer height of 10. If you go to a higher layer height, most probably there will be more significant differences on this. But again, every result to keep it comparable, we are doing it at layer height 10. So we see that direction 2 does not have as much effect, which most probably will be useful for creation of wall sections than the normal strength mixes. These are some flexural results on the sample where we have not done directional dependency, but we are just doing the print direction along the length of the beam, meaning it's just the most probably the strongest direction. And what we see is for the normal strength, with even when we incorporate like 0.3% of steel fibers or basalt fibers, we are in the range of 3.5 to 4 MPa. While for the higher strength performance concrete without fibers, these are all printed samples, not casted. Casted will have significantly higher numbers than the one that presented here. For the casted, for the lower water cement ratio mix, we are around 4 MPa without any incorporation of steel fibers, while we are incorporating 1.5% by volume of steel fibers. We are getting to about 14 MPa, while for casted it's around 16 MPa for the steel fibers one, while it's 8 MPa for the non-fiber ones. So for the mix, for the high performance concrete mix, the result that I showed you before without the steel fiber is the one that we selected. For the other mix, we selected a limestone-based binder, which we again characterized for the 3-directional strength. So here still again for the second type of mix that we are using, we still see that the direction 2 is significantly weaker. Before it was a different mix for the ones that I showed you, and this is a different mix. These are the 2 mixes we selected for the wall printings. So why does the direction 2 have that lower strength? We wanted to see it based on some mixes we did before. So you see that there will be this alignment of interfilament joints. This was a large solid section that we printed, and we poured out 2 cylinders out of it to reduce the actual equivalent area. Now that will have some detrimental effects to it, most probably. But again, we wanted to see like through DIC analysis, is there like strength concentration on points, which we obviously know should be, but we wanted to check like is it visible through actual testing procedure. So we tested this section under uniaxial compression. So again, this is after the test was done. There's a crack over here that is not as visible because of, again, it's like coinciding with the joints. So the crack initially started with this joints cracked first, while the sections could still take significant load, most probably because of the stable section. It was a larger stable section, and then the crack propagated in the perpendicular direction. So if you see, this is the interlayer joint direction. There are cracks in the interlayer joint directions also, and then later on the two cracks are on the perpendicular direction. The strength for this mix was 48 MPa in this direction of test, but when we tested this section, the strength were in the range of 20 MPa, most probably contributing to multiple factors like the cubes were perfectly cut into cubical shapes, so no joints that were, there were interlayer joints, but there were not stress concentration points like this over on the cubes. Second thing being, we cored out cylinders out of it, so there could be significant damage due to the coring process that we used. So we are again in the process of doing more structural testing on the infills, which we have not done yet, but we are trying to do that similarly. So again, this is the DIC image where you can see like this is an image taken around 50% of the cracking load, not even the peak load. When I'm saying the initial cracking load, it's when this joints cracked before even reaching higher loads. We can see like a high stress concentration on the filament joints, which was expected, and we can see that through DIC. In future, we are planning to like move this into a larger testing scale, where when I say larger, it's just going to be the heights are going to be significantly larger rather than the width and dimensions, because the dimensions right now we are using are in the range of, I think, 13 inch by 4 inch, which is again with the load taking capacity. If you go for like 7,300 psi, it will most probably hit the 400 kips capacity. So we are still going to go do similar sections, but with larger layer height to make it more height depth ratio. I'd like to acknowledge all the funding agencies through which we have gotten the funds to run our research projects. And I'd like to acknowledge all my graduate students and Andrea, who helped do most of the prints for this work. We are still in the phase of testing and making it more better. So any questions and any suggestions will be highly appreciated.